Okay, I think we should probably make a start. So, everybody, final session of the day. I'm delighted to have Scott Chapman from EPS presenting. Take it away, Scott.
All right. Thank you, Martin. And thank you everybody for joining for this last session today. So welcome to the afternoon. It's still morning here in the great state of Ohio in the Eastern time zone in the US. So earlier today we had our lunch and learn. It was really a breakfast and learn for me. So now I actually have lunch. So anyways, let's talk about what we're here for today. So this is the abstract. Presumably you've all read this, and that's why you're here today. If you don't know who EPS is, at Enterprise Performance Strategies, we do ZOS performance. We have Pivoter, our reporting and analysis software and service. We do education and instruction. We teach our ZOS performance workshops. Actually, today we teach them by Zoom, so they go around the world. We have done them on location around the world too, I guess. And we do a little bit of consulting, primarily around what we call our performance war rooms. And of course, we present at great forums like this at the GSE UK and share, and we do our own webinars as well. So if you're interested, hit up the link here at the bottom of the page. You can find our presentations and so forth there. So here's our EPS presentations this week. Peter's being a slacker or something, so he just did our performance spotlight this morning. We're talking about I/O and memory today, and then I'll talk about hyper dispatch on Thursday. So if you like what you hear, you can hear me again on Thursday. So this is our general agenda. I'm going to talk about what inspired this and why the only good I/O is still no I/O, and then some identification of I/O reduction opportunities, and then finally ways to actually reduce the I/O. So that's basically what we're going to talk about here. Now, the title of this presentation was really inspired by the Seven Dwarfs songs, which you may know as "Hi Ho, Hi Ho, It's Off to Work We Go." But in reality, they really mostly sang "It's Home from Work We Go." So for most of what they sing, it's from home we work we go. But at the end of the movie, they later return to work and briefly do sing "Off to Work We Go." So it really does have both in there. And yes, you have to go back to work. And this was a interesting trivia bit over supper one time, back when I was putting this together, because we had some discussion about the Seven Dwarfs, and my wife said, "Well, you guys probably haven't watched that anytime recently." And I was like, "Yes, I just watched it actually to verify that." Anyways, that's the source of the name, but the inspiration really for behind this talk is today we see many customers that have a memory-rich environment, but we also see where they also are doing lots of I/O. And so today this is one of those things that I'm like, you got all this I/O, or sorry, you got all this memory and you're doing all this I/O. Why is that? Now, I do say many customers have a memory-rich environment. If you're relatively short on ZOS memory, there's a few reasons why that might be. One, you already are actively leveraging that large amounts of memory that you have. Good for you. That's probably the minority of people. Maybe you have memory on the box that you've not assigned to the ZOS LPARs. We run into that a fair bit too. We look at an LPAR and go, "Wow, you're really running out of memory there." Maybe even paging, and we're like, and if I go look at all the LPARs on the box, I'm like, I know you have more memory than that, because on the Z16s, on the T01, minimum orderable memory is 512 gigabytes. So when I add up all the LPARs and I come to 200, I go, I know you have more memory someplace. So you can solve this, in worst case, paging problem by actually using the memory you already have. Now, a third option, primarily on the smaller machines, is that you didn't consider the opportunity cost of configuring less memory. So on the smaller machines, on the T02, the minimum orderable memory is 64 gigabytes. And I really kind of wish IBM would change that. I actually made that recommendation recently to the IBM hardware product manager, who's like, oh, but now people are going to be upset that you made them pay more. And I'm like, they shouldn't have to pay more. You're already shipping more memory than the 64 gig in the smallest configuration. So you could enable that for no additional charge. I'm not holding my breath, but it'd be really nice. And the fourth option we see is probably that you have lots of LPARs. We especially see this in outsourced environments, where of course the outsourcer may be charging you for memory as well. So in those environments, it's much more common to see more memory concerns. But I would say the majority of the customers look something like this, where in this particular case, the red here actually is the available memory. So this is the average available megabytes in central storage. It looks like over the course of a day here, no, actually over the course of several days. And that average rarely goes above, in this particular case, 50 gigabytes. They got another 100 plus gigabytes that they could be using, right? And this looks like the classic case of, if you remember back in, I think it was a Z13 timeframe, IBM said, hey, if you buy 3 times the memory on the next box, we'll charge you the exact same amount of memory, or the exact same amount for that memory. So people were buying 3x the memory, and then some of them never went and used it. So it was great that you bought it, but if you're not using it, you know. Now this is an average over the RMF interval. RMF will also record the minimum. And so we also like to look at the minimums. And in this case here, we do see that, oh, there are some times within some of those intervals where, yes, it's dipping down below 100 gigabytes. To be honest, a lot of these dips, especially if these are during heavy batch windows, I often figure are probably things like sort, making some use anyways of the memory that's available to it. So I generally don't worry too much about these, even if they're much deeper, just because if you have sort configured correctly, it will use memory, but won't use more than what's available to it. And so as we're looking at that, that's something we have to consider. But oftentimes my theory is, hey, if I could improve performance throughout the day at the cost of a few batch sorts overnight, running longer, maybe I don't care as much about those batch sorts overnight as I do about avoiding IO in general. Now, I said earlier, the only good IO is no IO. And yes, today IO is really, really fast compared to where it was, even going back 10, 15 years, right? But memory is really squared or really cubed fast. So today, in the majority of the subsystems that we see, you have oftentimes all flash subsystems, and new IBM DS8Ks now are also going all flash. I think EMC pioneered that, and said we're no longer going to put spinning disks in the box. And now IBM has gone that way as well, as my understanding. So if you're looking at these all flash subsystems, an IO now is down on average around a few hundred microseconds, right? So maybe a couple of hundred microseconds even. Interesting problem there is that our RMF measurements are often in 128 microsecond increments. And so that's a relatively large number compared to how fast the IO is, right? So that can, I wish that would be a problem that we could solve too. Now, if you have Z Hyperlink is advertised as being in the tens of microseconds range, because effectively Z Hyperlink acts much like almost like a synchronous coupling facility request, where the processor sits there and spins, waiting for that response to come back out of the DS8K or the whatever storage subsystem's cache. And the idea there is that because it's doing this synchronously and it's sitting and spinning, yes, you can get those IOs done if they're coming out of cache in tens of microseconds, which sounds really great compared to, hundreds of microseconds. But memory is a fraction of a microsecond. So you look at that and go, memory is still a lot faster than IO, and IO still takes CPU, right? if you're doing a traditional I/O via FICON, you're giving up the CPU to do that I/O, which likely means you're going to have to wait to be redispatched whenever that I/O comes back in. Now, I just said, well, it's only a couple hundred microseconds, but in CPU times, a couple hundred microseconds is a very long time, right? So, and very likely, you may not have your data and instructions in L1 cache. And so that's part of the benefit of Z Hyperlink too is, hey, because you're sitting there spinning, you don't have to do that I/O interrupt and your instructions and data are still in the cache. So you can just get right to processing that data. Isn't that great? Yes, that's great. It'd be even greater if you got it out of memory instead of getting it out of the memory of the storage control unit that is way over there. Get it out of memory that's right next to the processor. That'd be even better. Also, we should note that your software cost is driven by your CPU utilization, and your software cost is almost always greater than your hardware cost. So because of that, if we can reduce CPU by reducing the amount of time that's overhead for doing I/O, that's probably a good thing too. Now, I/O is not always the bottleneck today. I'd even say it's often not the bottlenecks, but it is still a common one, right? I was looking at a customer very recently, actually. They were complaining about their batch performance. And when I took a look at the charts, I'm like, huh, hey, so you're doing 100,000 IOs a second during your batch window. Maybe there's an opportunity there that we could make things better, right? So, and they were adding CPU to try and get batch done faster, which was helping batch get done faster because then they had less CPU delay. But another alternative might be avoiding doing all the IO in the first place. Now, you might say, but what about the DASD cache? I got a bunch of cache in my DASD control unit, so why keep it in memory on z/OS if I can just keep it in memory on the DS8K, for example? Well, the problem is the DS8K, it's actually, the max cache size only goes up to a little over 4 terabytes. Hitachi has similar numbers. They're in the single terabyte range for maximums. The Dell PowerMax, what we used to call EMC, those are larger numbers, but I don't quite understand them because I don't understand their architecture. There's cache mirroring, and those appear to be raw numbers, and I'm marking those as being marketing numbers more than effective numbers. Now, in comparison, today on the processors, we have tens of terabytes of cache. We have tens of terabytes of memory to cache that I/O, right? So in principle, anyways, we can put more in memory on the processor than we can in the storage control unit. So isn't that nice? And now with z/OS 3.1, our z/OS LPARs can go up to 16 terabytes. Whether you actually want to have a z/OS LPAR at 16 terabytes, that's probably a good question. But we are seeing customers with real LPARs that are over a terabyte. Those are becoming more common. I have seen at least one that was 4 terabytes. So these large memory configurations are certainly out there. I talked a little bit about Z Hyperlink just a moment ago, and Z Hyperlink solves a problem, and it's great for solving that problem, making those reads from cache faster. Again, I'd rather not even have to go ask the storage control unit. I'd rather get it out of memory on the processor because that memory is closer and will be faster than going off to the controller. Let's see, what else am I saying here? Oh, yeah. So the Z Hyperlink promises response times on tens of microseconds, which is much slower than your main memory. I tried to, as far as I know, there's not a published number for how long it takes on the Z16 to get the page of data, say 4K out of memory. But based on the published RNI formulas, based on the fact that L3 is said to have a 12 nanosecond or 0.012 microsecond latency, I'd say that an L4 processor cache miss, i.e. coming from memory, is probably on the order of 0.162 microseconds. You can probably ignore the 6.2 here as being overly accurate. The point is it's a fraction of a microsecond. So when you look at that and say it's a fraction of a microsecond compared to tens of microseconds, again, it's going to be much faster coming out of memory than it is coming across the hyperlink. And we know this just from the speed of light problem, right? So I say here, it's probably at least 15 times faster, which means it's 1/15 the CPU impact as well. So if you can avoid I/O, performance is improved, making the users happier to the degree, of course, that users are happy with better performance and to the degree that they notice, which of course may not always be the case. So, you don't have to spend time tuning something that's necessarily have to spend time tuning something to make the users happier if the users aren't going to notice. But if you can reduce CPU consumption, well, maybe that could reduce your software cost, and financial people are always happier with reduced costs. I said happier. They'll never be happy unless cost is zero, right? So maybe they'll just be less unhappy. And we can make better use of those unused resources. If we have memory just sitting around on the box that's not doing anything, I think that's a valid thing for management to criticize, that we got this memory and you're not using it, right? So now they'll have to go off and find something else to critique. So maybe you don't want to do that. Maybe you want them to just worry about your unused memory. But in general, I think we should avoid unnecessary I/O. And then my question is any read I/O really necessary? Of course, the answer is yes, right? I mean, we can't get away with not having to do any read I/O. But what if we made the assumption that, hey, maybe we had ginormous amounts of cache or ginormous amounts of buffers? Maybe we could dramatically reduce that, right? This is a slide I actually stole from Peter. Peter Enrico, my colleague, this is one of his slides. This is his point about trying to make customers happy, management happy, and your financial people happy. And there's a very tiny overlap area there where you can make them all happy. My argument is if you use memory to good effect to reduce I/O, you get closer to that center point there. Alrighty, so hopefully I have you all convinced that you should avoid I/O. The question is, how do we find opportunities to do that, right? Well, there's lots of places in the SMF data you can find I/O related data. Interestingly, these sometimes record data differently for the way the I/O is recorded is differently. The intervals that it's recorded on is different. The level that it's recorded on, i.e. perhaps on a data set versus a volume level, and whether that is from the perspective of the operating system or the perspective of the controller, all very different things. So it is a bit confusing, but there's lots of places where you can find find I/O measurements. For the purposes of saying, hey, I'd like to reduce the amount of I/O that I'm doing, those distinctions only, well, am I measuring start subchannels or am I measuring EXCPs? Doesn't necessarily matter a whole heck of a lot. You're just looking for relative volumes, right? So one of the things that's really interesting to me, though, is the 42s, because the 42s can give us stats on both a volume and a data set level. And these are relatively easy to deal with, okay? Now, they're not necessarily ideal, but they are pretty good. The 42s have both interval and close statistics at the data set level. You do have to be a little bit careful about the closed ones because those closed ones can encompass multiple, a longer time frame than what you might expect if all the preceding intervals had no I/O. So you do have to be a little bit careful about that if you're thinking, oh, I'm going to take these I/O numbers and divide by the interval length to get out a average IOPS number, an IOs per second number. That may not be valid for those close IOs in particular, or close records in particular. The interval statistics are controlled by the SMF interval, which ideally you'd have at 5, 10, 15 minutes. And if your SMF interval is greater than 15 minutes, please go change it to 15 minutes and sync those intervals. ideally, if it was me running a system today, I probably would be running at 5-minute intervals instead of 15-minute intervals. But the vast majority of shops, literally every time I go survey the systems that we have data from, I see numbers in about the 85 to 90% range of LPARs that have 15-minute intervals. So the vast majority of customers are using 15-minute intervals, and those are just fine for the most part. Other interesting point is that the 42s do have some IO response times at a microsecond level of precision. I have had thoughts about, hey, I'm going to do some analysis around those in comparison to the RMF numbers to get some better, some interesting reporting, I think, around comparing, the detailed at microseconds versus 128 microsecond increments. I haven't done that yet, to be honest with you. And it does have details about cache hits and misses. So overall, they really are an excellent source for understanding what is doing I/O. They can be a little bit voluminous depending upon your situation, but still a good source. So I have a couple of example cases here. Now, in this case, here I have the I/O start subchannel rate by service class period over time. And in this particular case, the left-hand side of the chart here is starting at 6 a.m. And so during our primary daytime hours here, what we see is most of these service classes aren't really doing much I/O at all, but we have a couple of service classes that are doing basically 1,000 IOPS a piece, or just under that. So, and because the customer CPU was highest during these hours, the higher I/O rates later in the day, there was probably batch related, right? I don't necessarily care a whole lot about. These numbers come directly off from the 72s. These numbers then, therefore are very easy for me to get, very easy for you to get and report on as well. And then I took a look at the storage groups. So these numbers come off from the 74s. And here we have one storage group that's running a bit over 1,000 IOPS during the day, right? And actually, there's another service class here, or sorry, storage group here that's even busier at times. So it's interesting to me that we see this storage group that's also right around that number. So oh, that's right. These are not a storage group. These were in none. So so there were some volumes that were not part of a storage group, and that's what the none is. So those could be system related things, right? Maybe they're spool volumes or something. I don't know. I thought I'd start with the storage groups. Hopefully the application IO is there. When I went and looked at the logical volumes with the highest IO rates, I saw this particular volume SM2124 is much higher than all the other volumes, right? So I have a single volume here, and this is over the course of the entire day. So this IO rate is averaged over 24 hours, which is not a great thing to do, right? Because it's not showing us where our peaks are. Our peak is no doubt much higher than this. It probably wasn't that, constant 24 hours, but it does give us a sense for which volumes did the most IO overall over the course of the day. We could have easily have also labeled this in just total number of IOs, right? So whatever 375 IOs per second times, what is it, 86,400 seconds in a day, that's total number of IOs. We could put that number there, but the shape of the chart wouldn't change, right? But what I'm interested in is this SM2124. So I went to look at that particular volume, and lo and behold, that particular volume was actually doing over 1,000 IOPS during the day, during that time frame where we saw their that was the peak of their time for their CPU consumption, and they had a couple of these storage groups that were doing over 1,000 or around 1,000 IOPS. This one volume at times was doing over 1,000 IOPS. So this does make me wonder what's on this volume. Now, unfortunately for this particular customer, We didn't have data set level decollect data for them. We did have volume level decollect data, so I could tell how much data was on the volume. So this is a 25 gigabyte volume, so that's a mod, what is it, mod 27 or some such. And the allocated gigabytes on the volume, though, is only 1.4 gigabytes. So here we have something that's doing over 1,000 IOPS. And notice that these are all reads. There's no writes, basically, to this volume. It's doing a whole bunch of reads. There's only 1.4 gigabytes of allocated data on that volume. So I don't know what that data is, but it could easily fit in memory. And, you know, 1.5 gigs of memory to avoid 1,000 IOPS during the day sounds like a really great trade-off, right? So here's another example. In this case, we're coming at it from the SMF42 perspective. So here, what I did here was we took the SMF42 data, and because we have it at a data set level, and because there are certain patterns we know in terms of data set naming conventions, in terms of the data set organization and so forth, we can get a pretty good idea of what those data sets are used for. And it's fairly common if you have a DB2 shop that you're going to see, gee, a majority of our IO is going to DB2 objects, right? And that's what we see in this particular case here. Now, in this case, we actually did label this chart in millions of IOs. So this is millions of IOs done over the course of the day. Again, we could have averaged it to seconds, but the shape of the chart wouldn't change. And the other important part that we have here is we have a breakdown between read and write. And again, the vast majority of the IOs going to these DB2 objects all day long are just read IOs. And again, this is also not unusual for a lot of shops. We look at it, there's a lot more read IOs that are happening than there are write IOs. And like I said, you get a pretty fast tail off in a DB2 shop, in particular on these other things. In other shops, you know, we have seen shops that are very VSAM oriented, and maybe the VSAM ones then will be much larger. If they don't have DB2, then DB2 goes away, and all of a sudden you're storing your application data in VSAM. You have a bunch of VSAM IO instead of DB2. The same sort of idea, though, right? So now, if I drill down into this a little bit, in this particular case, now we're looking at the top data set IO counts by the data set usage. So for DB2 objects on this particular system here, what was the breakdown in terms of the top data sets? Now, I've blurred these out to protect the innocent, but we can see that if you are a DB2 person in your shop and you look at these things, you will be able to then go back and figure out, well, what table or index is that really related to? What you see here is actually an index space, so there's actually an index there that's being hit. We may see table spaces here or as well. But again, we look at this and we got millions of IOs here going to this one index, and you notice here that the cache hit percent is very high. So yes, this index is staying there in the storage controller, in the cache, in the DS8K or whatever DASD is in use here. But wouldn't it be better if we just kept that in memory, right? So in this particular case, we actually did have data set level decollect data from them as well. So when we went and did that, this report marries up the 42s with that decollect data. And what we see here are things like, here's how many read hits we're getting, here's how many megabytes of data we're reading from this individual data set here. And actually this data set is spread across 2 volumes, and we've summed up the total size here, and here's the total size of that data set. So across the 2 volumes that this thing is spread across, it totals 569 megabytes. And yet we read 4 terabytes of data out of that index today. That sounds like something that maybe we could do a better job of keeping that in memory, right? If you don't have 569 megabytes of available memory, we have a bigger problem, right? So, and if you go down through this list, we did try to do some fun things here in terms of ratios and stuff like that. But you can see that in this particular example anyways, yes, we have some that are like, oh, look, 4 gigabytes. But again, if you have hundreds of gigabytes of memory available, even 4 gigabyte objects don't sound so big anymore, right? So this is a very, very interesting report when we start looking at, when we start seeing things like this, right, where there's a whole lot of read activity, we can then drill down on what data sets are doing it. And even if we have the decollect data, it gets even more interesting because now we can see for those data sets, how big are those data sets? And then we can start targeting data sets that are doing a lot of I/O and are relatively small. Now, the question is, what do we do about them, right? And the easy answer is DB2. So DB2, you've been able to do this forever. Basically, pin the objects in the buffer pool. Now, again, you've been able to do this forever. Just make the buffer pool big enough to hold the entire objects. So on DB2 systems, it's not unusual today to see systems with hundreds of gigabytes of buffer pools. When I look at a system and I look at their total buffer pool size and I see something that's in the single digit gigabytes, I'm actually very confused by that if it's a production system, right? So big buffer pools, not unusual today. Now, there are, I would say, new, this page steal none came out circa DB2 version 8, maybe, maybe 7. I don't remember. It was a long time ago, right? So the page steal none basically indicates to DB2, you believe the buffer pool is big enough to hold all of the objects in the buffer pool. That doesn't mean that DB2 won't steal pages from it. So page steal none sounds like you're saying DB2, you can't ever steal pages from it. That's not what it means, though. And it also doesn't mean that the pool is read-only. So what this actually does is it will trigger DB2 to use async prefetch to preload the objects the first time the object is referenced, right? So interesting part about this is, oh, DB2 starts up for the first time for the week because you recycle DB2 once a week if you're still into that mode, or once a month, or however, whenever you IPL, right, would be a better answer. And the first time you reference an object that's in the buffer pool with this page steal none, DB2 says, oh, I'm ready. That the buffer pool should hold all of this data, and it will go prefetch all of the data into the buffer pool, and then it's all there waiting to be used, right? The great thing about that is, when does that happen? Well, usually around your DB2 recycle or your IPL time, when hopefully you don't have a whole lot of other activity going anyways. So yes, you get this burst of I/O to read all of that data, but then it's sitting in memory waiting to be used during time frames where maybe you care more about that performance. Now, there is an interesting problem here. I believe this problem still exists. You can't use page steal none and frame size 2 gig together, which is a shame. None and 2 gig will be treated as LRU in 2 gig, so you want to use none and 1 meg instead, which again is a shame for supersized DB2 buffer pools, because those supersized buffer pools, having those be 2 gig pages is probably not a bad thing. But if you're trying to do page steal none, that's not going to work so well. Again, last I knew, this was still an issue. If you're looking at doing supersized buffer pools and looking at 2 gig and you have page steal none, go double check this. Like I said, last I knew, this was still an issue, though. Remember also to page fix your production buffer pools at least. Probably your dev test buffer pools as well, because this results in a CPU reduction for every I/O to and from the buffer pool. If the buffer pool is not page fixed, when it does an I/O, the page has to get fixed, and then DB2 will unpage fix it when the I/O is complete. So that's both on reads and writes. So by page fixing the buffer pools, you avoid doing a page fix and unfix for every I/O for every that's going to in or out of the buffer pool. So this is important from a CPU reduction standpoint as well. And again, if you have sufficient memory on your systems, why wouldn't you page fix dev test as well to avoid that? Yes, the impact there is probably smaller because you're probably running many fewer IOs out of dev test, because especially in dev, where you just have kind of sporadic workload. If you have a test environment where you're driving, maybe even not production, but significant volumes for performance testing or regression testing or something like that, maybe it's more significant there. But again, if it's not terribly, even if it's not terribly significant, if you have the memory to do it, just go ahead and page fix them. So the other point here too is with DB2, if you're in a data sharing environment, then you also have group buffer pools as well. So the general rule of thumb for the group buffer pool size as a starting point is the sum of the local buffer pools divided by 3. If you want more details about that, go search out Robert Catterall. That's where I got that number from. I did ask him about that within the past 5 years to say, hey, is this still a good starting point? And he said, yes, that's still a good starting point. So the goal there is to avoid directory entry reclaims. But if you have buffer pools with very little update activity, so for example, they're basically these big read caches, well, then maybe you don't need quite as much group buffer pool cache for that. And you might also consider this idea of group buffer pool cache no for those buffer pools as well. Basically, at that point, the group buffer pool is just used for cross-invalidation. The writes will suffer though. But if you have, again, if you have one of those objects that's essentially read-only, and you have a bunch of those objects in a buffer pool, and those objects very rarely get updated, then GBP cache no may be perfectly fine. Yes, the writes will take a little bit longer, but if you're doing a very tiny amount of writes to those objects, doesn't really matter then, right? The other idea is that you could use group buffer pool cache instead of local buffer pools. So instead of having really large local buffer pools, have a really large group buffer pool, which could save on the amount of memory you need overall. Okay. You can do this with the group buffer pool cache all on the object level, which says the pages will be copied to the group buffer pool as they're read, regardless of read-write interest. Okay, usually they only go to the group buffer pool if there's inter-system read-write interest. GBP cache all basically says put them all over there, right? Now, here you'll end up with a benefit similar to Z hyperlink without actually having to implement Z hyperlink. So that's not bad. And it's probably actually a little bit better because DB2 is going to be checking the buffer pools anyways before it issues the IO, right? So if you think about it, DB2 is going to say, oh, do I have this in my buffer pool? And if the answer is no, then if you have Z hyperlink set up, well, it's going to drive that Z hyperlink IO. Even better would be, oh no, we're just going to go get it out of the CF. So instead of driving an IO that acts like a synchronous CF lookup, we could just drive a synchronous CF lookup. So I like this idea too. I mean, even better is to have it in the local buffer pools. But if you're constrained on ZOS storage and you did it in the group buffer pools, I think that's an okay solution as well. IBM did a study on this several years ago now, might have been 10 years ago, before memory was as big as it is today even. And the idea there, they were trying to show, hey, instead of having these two really big local buffer pools, you could buy less memory, just put it on the coupling facility, and then it would you could get this very, very similar effect. The issue of that, of course, is you need memory on 2 CFs. So if you're just in a two-way data sharing, I'm not sure that it's really that much different. If you're in like a 3 or 4-way data sharing environment, maybe it starts to make more sense, but something else to consider anyways. Unfortunately, I know more about DB2 than I do VSAM. I had to dust off my almost 30-year-old VSAM tuning memory here. So I apologize if I have VSAM gets a little bit of a short shrift here, or maybe not perfectly described here. But basically, there are 4 types of buffer pool management for VSAM. So NSR, or non-shared resources, LSR, local shared resource, GSR, global shared resource, which is no longer used, and RLS, which is essentially the newness, which is the record level sharing. And new is not very new in this case. Now, interestingly, these are not part of the VSAM dataset definition. These are actually set on open. And if you want more information about this, go take a look at the VSAM Demystified Red Book, where you can find more information about all of these. At a very high level, though, the VSAM NSR is the default batch access method. And basically, you tune the buffers via buffni, buffnd, so the buffer numbers for indexes and data on the JCL DDAMP parameter. And the idea here is that if you're doing direct access, then you just want 1 per concurrent request, which we call a string for reasons that I don't remember. And for index buffers, you want enough to hold the entire index set, which is really the number of index records minus the number of data CAs. For sequential access, then you probably want data buffers up to the number of CIs in a CA, and that's probably fine. The index buffers are probably immaterial if you're doing sequential work, and skip sequential generally works similar to direct access. And unfortunately, over-specifying buffers for VSAM NSR really has very minimal memory impact, but it also provides minimal additional benefits as well. You're still going to do I/O. Now, you could also do SMB, system managed buffering, which basically says, hey, I got some NSR stuff. System, you go figure it out. The data set must be SMS managed. It must be extended format, which that may stop some of you. And basically, you set it on the AMP parameter or on the data class. And then system takes into consideration the storage class bias. And you can also set it yourself directly. This may provide better performance than plain NSR, but frankly, to me, it seems similarly arcane. Maybe more so if you let it rely on the service class or data class, because then it becomes even less transparent to the application programmer. My recollection from when I was doing this in the mid 90s, this provided very little additional benefit to us. Now, what is potentially beneficial is LSR. LSR, or local shared resource, is primarily used by CICS and IMS, but there's also the old batch LSR subsystem, which can extend it to batch work too. This can be beneficial in specific situations, and it can work with data sets that are non-SMS managed. This really works for the specific situation of you have random access to the same data over and over and over again. So it does not do read ahead for sequential access. It can defer writes, but if you're accessing those same little pieces of data, same records over and over again, batch LSR can be useful. Now, the controlling address space creates 1 or more buffer pools that are shared amongst multiple VSAM files. Again, there are limitations to batch LSR, but it can be beneficial. I do remember that when we were playing with this, again, back in the 90s, when I/O times were also much longer, batch LSR was definitely beneficial to us in those situations where we could use it. Now, even better than that is really VSAM RLS. So this allows concurrent access at the record level from across the sysplex while maintaining file integrity. This is managed by an address space called the SMS VSAM address space, and the buffers are managed by SMS VSAM and shared amongst all the address spaces on the LPAR that are using that VSAM data set. Then one of the nice things here is it can eliminate the CICS FOR regions and the inherent function shipping that may be there. Your files do have to be SMS managed, and of course, it does require a coupling facility, and it has a lock and a cache in the coupling facility. And recoverable data sets, batch access can be in read-only mode, which that may be a problem in some cases, of course. But the VSAM RLS does make VSAM processing look a little more like DB2, and this can certainly result in a performance improvement and I/O reduction compared to LSR, but again, it is situationally dependent. However, there are other things you can look at as well. So for example, your VSAM KSDSs that are being referenced from CICS, you might consider making that CICS maintained data table. So basically the file is cached in data space inside a CICS. You don't need to make application changes. There are some caveats, of course. Go read about it on the fine web. And the file cannot be in VSAM RLS. And if you have read-only files, well, then user-maintained data tables may be a fine option as well. Finally, I should point out for all of these things, if you can make application changes, those may be even better than buffering to avoid accessing the database. There are third-party products. I mentioned one here that can help with this. But your application can do those lookups to yourself potentially as well, right? So maybe you can write some application code to do this. Interestingly, again, back in the 90s when we were doing this, we ended up writing, I ended up actually writing some code that did exactly that, that stepped in front of one of the VSAM files that was getting hit very heavily. Even with batch LSR, it wasn't enough to make it better. I ended up writing a little cache module that sat in front of that, and the people that were using that file were suddenly very, very happy once that went in. So removing execution, and the other point is, if you don't need to do a lookup, if you can just hold on to that, then that can always be a performance win, right? My example here is, do you always have to look up, what the state name is for OH? OH is always Ohio. It was for the last record. It is for this record as well. And if your business is primarily in Ohio and you're processing primarily records from Ohio, maybe you could just say, oh, the last thing I did was OH. I know what that one is. So avoiding unnecessary lookups is always good too. Now, one thing that actually shows up sometimes interestingly in terms of I/O is the catalog. There's basically 4 different levels of different types of caching you can do for your catalogs. So if your catalogs are showing up as being significant I/O consumers, the starting point is up here at ISC. The best answer is probably down here at RLS. ISC is the default, the in-storage cache. Most people today really should be at least at the catalog data space cache, which is a VLF managed data space. This is an LRU cache. You define it in COF VLF, and the default storage used is only 16 megabytes. It does have a max of 2 gigabytes. So you're a really large catalog. You can't put the whole catalog necessarily in memory. So you do have some limitations there. Now, the step better than that was ECS. And ECS was enhanced catalog sharing. This avoids some of the VVDS volume restrictions. It works with CDSC. So this is a better answer. It basically cached some of this from the catalog stuff in the CF to share it better amongst the systems. However, a few releases ago, and by few, I probably mean 5 or 6 of the operating system, they came out with RLS support for the catalog. Now, this is expected to be even better than ECS and can potentially get to larger cache sizes as well. Again, requires a CF because you're using RLS, but this is what you should be looking at today to be able to really best cache your catalog IOs. Similarly, we occasionally see HSMs, CDSs, causing IO problems as well, or at least doing a bunch of IO. And similarly to catalog, you can actually use vSAM RLS for the CDSs as well. I didn't know that until I was actually researching this for this presentation. So this is a good option too. Size your RLS buffers appropriately. Again, size them generously if you have the memory for it. And this can improve your overall HSM performance as well, because again, memory instead of I/O, better performance. Now, you may be saying, Scott, I don't have a CF. And my answer is, you could though. The best practice is, of course, to run the coupling facility LPAR on a dedicated ICF engine, but you can run it on a GP as well. And we have customers doing this in production. In some case on surprisingly small systems. I wouldn't recommend this for high volume data sharing. But if you're just trying to get RLS up and running to be able to do some caching to avoid some I/O, guess what? It's probably going to work okay. Now, in the old days, we tried to desperately avoid this, right? Because, oh, I'm running on a GP. I paid expensive money for that GP, and my software cost is based on the total capacity of my machine. And so because of that, I don't want to waste any of that capacity doing something like coupling facility, right? Well, today you should be paying for the majority of your software based on consumption, not on the total size of your machine. And you're really not going to consume anymore because you stood up a CF LPAR. Now, it shouldn't, I say it doesn't directly impact your software cost. Every time you stand up another LPAR that's sharing a CP, there can be inter LPAR effects, and the sharing effects across multiple CPs may, of course, result in some slight inefficiencies. For a CF LPAR that's doing a bit of caching for your RLS stuff, you're probably not going to be able to measure that. So you're probably not going to notice that in terms of any sort of software cost impact. If you do, it's probably so minor that you're going to look at and go, I got so much better performance, I don't necessarily care about that. The other point here too is that if you're a Sysplex in a box, right? So you don't have two machines, you only have one machine. Why am I setting up a coupling facility in a Sysplex, right? Well, you can have a Sysplex in a box and get the benefit of that coupling facility in terms of supporting RLS. And that may be quite acceptable to have a single CF instead of the normal recommendation for parallel Sysplex of having dual CF, so you can do failover and all that sort of stuff. If everything's running on one machine and you didn't have a CF before, you probably don't care about that. So having a single CF running on a small share of a GP may be perfectly fine. Now, I'll say caveat again, best answer is always to have a dedicated ICF engine, but in some cases, running it on a GP is perfectly fine. By the way, the more CPs you have, the better, the less likely that's going to be a problem. However, I will say I have one customer that is running an entire Sysplex on a one-way machine that includes multiple LPARs and includes a CF LPAR all running on a single GP. So it can work. I'm not saying that's a good answer. I'm not saying I would recommend that to anybody. More than one CP, please, but I'm just saying it can work. Okay, in the last 5 minutes here, I have just a couple of more topics here, I believe. Sequential files, for the most part, I haven't seen a whole lot of concern about this since the 90s. Of course, as soon as I said this for the first time, somebody then emailed me later and said, oh, but Scott, I do have a file that's causing me trouble that's sequential. Sorry about your luck. One thing is, of course, to consider compression to decrease IOs. And of course, there are now newer compression options since the 90s. We now have ZDC and things like that. You can consider raising the BUFNO on QCM from 5 to 10 or 15. Again, this is one of those decreasing amounts of benefits, though. You do want to be sure to use system-determined block sizes, which are usually around half a track. Again, not something we see a whole lot of problem with today, but occasionally I still come across stuff I'm looking at and going, oh, we got 800 byte block on that. Nice. Striping was very useful in the SCON days, and especially with non-RAID disk, maybe less useful today. It's been a long time since I've actually tested that myself. I did test it after FICON at one point. That was a long time ago. There was a minor benefit at that point even with FICON. So there may still be some benefit from striping it, but definitely going to be smaller than it used to be in the old days. Your sort products can make good use of memory for in-memory sorts. This has been true for decades, of course. Just make sure you have your parms right. Don't let it run away with all of your memory. So having some control over it would be good. I haven't seen many problems with sort running away and causing detrimental effects these days, but just make sure you're doing things right. The new SORT-L facility on the Z15 seems to allow even more improvement. And there's this DF sort exploitation called IBM Z sort. I'm thoroughly underwhelmed by it from what I've seen. So, yes, there's an IBM test out there that says, hey, we did a 44 gigabyte sort and it resulted in a 50% reduction in elapsed time and a 40% reduction in CPU versus an in-memory sort without using Z-sort. But if you use sort work, it was actually the same amount of CPU as Z-sort, although it took almost 9 times longer. So yes, there's a performance savings, but there really wasn't a CPU savings associated with that. I had a customer that was playing around with this that was confused why they were not seeing the results that they expected. And so they contacted me and said, hey, this is what we're seeing. Can you look at our data to see if you see anything different? I'm like, nope, it don't look like it's helping. So yeah, so far I'm thoroughly underwhelmed with this. And it does require the recommended planning number is need twice as much memory as the size of the data set. If it's a small data set, not a big deal. But if it's a small data set, it doesn't take that long to sort anyways. So I'm a little underwhelmed. And I haven't seen a sync sort benchmark from that. So here's my summary. Many, but not all systems are memory rich today. And if you're not, I think you should be. I made a statement here recently that I'd like to see z/OS be the in-memory operating system. DB212 came out. IBM said DB2 is an in-memory database because you can cache everything. Well, I'd like to see the more stuff be in memory than just DB2, and you can take advantage of it for other things as we've shown here today. And if you do that, you'll improve performance, you'll potentially reduce your CPU, and thus potentially reduce your software costs as well. SMF has a plethora of data and a number of records to help you find where your I/O is. The SMF42s are a good place to start looking. Strongly recommend that. And once you've found your I/O, then figure out how to keep that data in memory. So with that, I think we're down to questions if there are any. And if not, I'll say, please remember to submit your session feedback. I lost the chat. So, oh, there it is. Oh, somebody has a comment. Oh, that was Martin Packer has a comment.
Yeah. And I hit the button on it in case you covered it, Scott. In which case I'd have deleted it. So no, it's just back. You don't need to go back to the slide. It was just a comment that Kix data tables are still around as a way of avoiding going to VSAM in particular. So that was just another example, really. Okay, right. Of the people who are here, who stayed all the way through from the beginning, almost entirely, are there any more? Well, are there any questions, any more comments that people would like to make at this point? And Scott, could you just put your email address in the chat so people who wake up in the middle of the night with a burning question can send it to you?
Yep, and it's on the first slide as well. So
perfect.
You'll get the slides. It should be. Whoops, that's the wrong slide. Sorry. Whoops, that's the wrong slide. There's the appropriately branded slide.
Yes, you've done what we all do, which is slap the appropriately branded on the front, and yes, the minimal effort and worth it or something. Okay, right. If there are no more comments and no questions, I think we'll literally call it a day. So thank you, Scott. This was really good, I think.
Oh, thank you for having me, Martin, and nice seeing you.
I was just gonna make one comment on Sort L, not to be defensive about it. If you talk to Dave Betton about it, he basically says it works best when you've got the vast majority of the data actually in memory, which for I think it was a 44 gig case, not quite so easy. Although nowadays we sell machines, as I said this morning, up to 40 terabytes to throw. So
Yeah. Well,
not that I know
and like
anybody who has that.
well, yeah, I don't know you sold any of those yet. I understand a lot of those are destined for Linux,
Yeah.
large Linux environments, but yeah, I mean, it's certainly common though to see hundreds of gigabytes of available storage on ZOS.
Oh,
So
absolutely. Yeah, I think that's our experience as well. One thing we do plot, by the way, is the minimum, which I normally try and explain to
right,
people what the minimum is compared to the average, because
that was
yeah,
this slide here. So
that's right. And I was
yep,
paying attention. I'm just saying I'm endorsing that as an approach. Comparing it to the average is kind of useful. But anyway,
it can be useful.
yeah.
Like I said, I usually don't worry too much about these dips because my general inclination is those are often sorts. Um,
Well, exactly that, and that's actually I'm not saying you're doing it wrong because I don't think you are. That's where we actually slap the average and the minimum on the same slide, so then we can go. You know what? There is some deviation because of precisely what you've said, because we do it by time of day as well. So, okay, I think there's nothing more from anybody. We'll call it a day.
okay, sounds great. Y'all
Thank you,
have a great
everybody.
rest of your day.
Likewise. Bye bye.